Black screen. The sound of cosmic static, white noise, ethereal and haunting. Gradually, images emerge from the darkness. A field of stars. A radio telescope, silhouetted against the night. The static evolves into a haunting, almost musical tone, as if the universe itself is humming. Ext. Very Large Array, VLA, Socorro, New Mexico, night, stock footage. A sprawl of enormous white dish antennas stretches across the New Mexico desert. Some are aimed at the zenith, others sweep the horizon. The landscape is barren, absolutely silent except for the gentle turning of the dishes. Close on a single dish, approximately 25 meters in diameter, rotating with mechanical precision. The sound design shifts, radio waves being heard as a faint whisper, like tuning through an FM band. For over 60 years, humanity has asked one of the greatest questions ever posed: are we alone? We've built magnificent machines to listen for the answer. Radio telescopes, scattered across the planet. Pointing at the sky. Waiting. Listening. Montage. Iconic SETI history. Frank Drake started the search in 1960. Operation Ozma. Looking for signals from Tau Ceti and Epsilon Eridani. He was listening for a narrow band signal, a kind of cosmic whisper, concentrated and pure. And we've been searching ever since. 60 years of listening. The radio telescopes have grown more sensitive. Our computers more powerful. Our databases more comprehensive. And yet, nothing. A visual representation of radio waves emanating from a distant civilization. Perfectly narrow, like a laser beam cutting through the void. We were looking for something very specific. A narrowband signal. A tightly focused beam, like a cosmic needle in the haystack. Scientists reasoned, nature doesn't naturally create such narrow beams. So if we found one, it had to be artificial. Intelligent. Alien. For decades, that was the assumption. Look for the spike. Look for the anomaly. But what if we were wrong? What if the signal was there all along, hidden not by distance or silence, but by something far more insidious? Wide shots of various radio telescopes. The Arecibo Observatory, before its collapse, the Green Bank Telescope, ALMA in the Atacama Desert. Each one a monument to human curiosity. The music swells, hopeful but undercurrent of melancholy. Decades of data. Millions of star systems analyzed. And nothing. No laser beams. No clear messages. No unmistakable sign of another civilization screaming, "We're here." Scientists began to whisper. Perhaps the great silence is the answer itself. Perhaps we are truly alone. But there was one problem with that conclusion. It was based on a single, unexamined assumption. A stark, simple graphic appears, a narrow vertical line representing a signal. The narrowband assumption shaped the entire SETI enterprise. We built our filters, our algorithms, our detection methods around this single idea. But what if that assumption missed something? What if the universe is far more complex than we thought? Is not a story about absence. It is a story about what we failed to see. The hidden gatekeeper. Imagine an alien civilization, much like us. They've built their own radio telescope. They send a message into the cosmos. A signal, carefully crafted and transmitted. It leaves their planet, traveling at the speed of light. A perfect, narrow tone. Just like Frank Drake predicted. And then, it encounters something unexpected. The signal travels outward from the alien sun. But surrounding that sun is a turbulent, roiling cloud of plasma. Solar wind. Magnetic fields. Coronal mass ejections rippling outward. The signal enters this fog, and immediately, it begins to distort. The sharp, narrow beam blurs. It scatters. It fragments into a diffuse, broad spectrum of electromagnetic noise. Every star has an atmosphere. Not the kind Earth has, an atmosphere of ionized gas. Plasma. Magnetism. We call it the interplanetary medium, or IPM. This weather system varies wildly depending on the star. Some stars are calm and predictable. Others are absolutely chaotic. A scientific diagram appears, showing the structure around a star. Layers of ionized particles, magnetic field lines, spiraling patterns. The interplanetary medium isn't empty. It's a soup of charged particles, mostly protons and electrons from the star's atmosphere. When a radio wave travels through this medium, it gets scattered. It's like trying to send a laser beam through a room full of smoke. A series of graphics showing radio wave propagation. Left side. The original signal, a perfect 1 Hz tone shown as a narrow spike on a frequency graph. Right side. The same signal after traveling through the IPM. The spike broadens into a wide, diffuse hump. From a needle to a haystack. Red text appears. Smeared signal, now invisible to narrowband filters. This is the hidden gatekeeper. This is why we haven't found them. A sharp, narrow signal, the kind we designed our filters to find, arrives at Earth smeared across a wide frequency range. Our algorithms look for spikes. They ignore the broad, faint hum. It's like searching for a specific voice in a crowded auditorium. You're listening for a clear, distinct tone. But what arrives is a faint whisper mixed with background noise. And your ear, tuned to find clarity, misses it entirely. Beautiful, almost dangerous footage of the sun's corona. Coronal mass ejections erupting from the surface. Magnetic loops twisting and releasing energy. The severity of this effect depends on the star. Our sun has a relatively calm, predictable IPM. Solar wind and occasional eruptions, but nothing catastrophic. But not every star is so well behaved. Some stars, especially the smaller, dimmer ones, have IPMs so violent, so chaotic, that any signal passing through them would be utterly mangled. The M-dwarf problem. Here's a sobering fact: 75% of the stars in our galaxy are M-dwarfs. Red dwarfs. Small, cool, and extraordinarily abundant. And here's where it gets interesting. These are some of the best candidates for habitable planets. Dr. Jill Tarter, former director of SETI Institute. M-dwarfs are exciting for the search for life. They're stable for trillions of years, which is great for evolution. And they're everywhere. If you want to find an inhabited world, statistically, it's probably orbiting an M-dwarf. Stunning close-ups of M-dwarf stars from satellite imagery and artistic renderings. Their surfaces are violently active, flares erupting, magnetic storms visible as dark and bright regions. But here's the problem. M-dwarfs are volatile. They flare frequently. They have intense magnetic activity. Their IPMs are far more chaotic than our sun's. If an alien civilization evolved around an M-dwarf, any radio signal they transmitted would encounter a fog of unprecedented turbulence. The signal wouldn't just be smeared. It would be shattered. Signal path from M-dwarf and M-dwarf star, bristling with activity. A radio signal is emitted from a planet in its habitable zone. The signal enters the turbulent IPM. Unlike the previous example, the distortion is severe. The sharp signal broadens dramatically. The frequency profile becomes a wide, noisy mess. Think about the statistical implications. 3/4 of the stars in our galaxy are M-dwarfs. If life is common, and if the inhabited planets statistically orbit these smaller stars, then the majority of alien civilizations we might detect are transmitting through the most challenging medium possible. We've been searching for signals that would be clearly detectable. Clean. Narrow. Obvious. But if those civilizations are real, their signals aren't obvious. They're buried. Hidden beneath layers of cosmic static. This is the M-dwarf problem. The places where we're most likely to find life are the places where signals are hardest to detect. It's as if the universe is playing a cosmic joke on us. We know where to look. We just haven't known how to listen. Here's how scientists made a breakthrough. They didn't look to the stars. They looked at home. Our deep space probes, Voyager, Rosetta, and others, are transmitting radio signals. Weak, deliberate signals, traveling through our own solar wind. By tracking how these signals degrade as the probes journey farther from the sun, researchers could quantify exactly how much our star's IPM distorts radio waves. A researcher at a desk surrounded by data. Graphs showing signal degradation. Frequency charts displaying the broadening of radio frequencies. Close on a monitor, a narrow band signal at the transmitter, gradually broadening as it travels through space. We have a natural experiment playing out right now. The Voyager probes are transmitting X-band signals at 8.4 GHz. As they travel through the solar wind, the signal broadens. We can measure this broadening precisely. Now we have a calibration. We know exactly how much the sun's IPM smears a signal. A technical visualization of Voyager's signal strength over time. Graphs show the signal being transmitted narrowly, then broadening as it travels outward. Mathematical equations appear on screen, showing the relationship between IPM properties and signal distortion. This led to a critical realization. We can predict how much any star's IPM will distort a signal, based on the star's properties. Solar wind density. Magnetic field strength. Flare frequency. Age of the star. All of these affect how much a signal gets smeared. And for the first time, we had a mathematical framework to describe it. A side-by-side comparison of signal distortion around different star types. Left. A sun-like star. The signal broadens modestly. Middle. A moderately active M-dwarf. The signal broadens significantly. Right. A very young, very active M-dwarf. The signal broadens dramatically, becoming almost indistinguishable from background noise. Dr. Kat Barger, SETI Institute researcher. The key insight is that we now have a predictive model. We can look at a star and say, a narrowband signal from that star would have a scattering measure of X, which means it would broaden to Y bandwidth. And that's exactly the kind of signal our current detectors miss. Scientific progress. Quick cuts of data analysis, computer simulations, scientific papers being published, researchers discussing findings. The mood shifts from mystery to revelation. Discovery. So we weren't looking at a fundamental failure of the search. We were looking at a failure of perspective. The signals might have been there all along, buried in the data we'd already collected. Hidden by our own assumptions about what we were looking for. Now, with this new understanding, we had to ask ourselves, what would it take to actually find these smeared signals? Rethinking the search, we're entering a new era of search. Not a new era of listening, we've been listening for decades. A new era of understanding. Understanding what to listen for. We have two major advantages now. First, we have better telescopes, more sensitive to faint signals. Second, and more importantly, we have better algorithms. Artificial intelligence. Machine learning. AI and machine learning, a visual representation of machine learning algorithms. A neural network visualization appears, with connections lighting up as patterns are recognized. Data flows through the network. Complex patterns emerge. Signals are classified, categorized. Dr. Jill Tarter, former director of SETI Institute Machine Learning, is revolutionizing how we search. Traditional algorithms are rigid. They look for specific, predetermined patterns. I can learn what a dispersed signal looks like, across a wide range of parameters, and identify it even when it's faint and broadened. Old versus new approach. Left side, traditional SETI approach. A narrow, rigid filter scanning through frequency space, looking for specific spike-like patterns. Right side, AI-based approach. The algorithm learns the shape of a broadened signal, the fingerprint of an intelligent transmission hidden in noise. The search becomes three-dimensional, adaptive, intelligent. The difference is profound. Imagine you're looking for a face in a crowd. The old approach. Look for a specific, perfectly clear face. If the face is obscured, masked, or partially hidden, you'll miss it. The new approach. Machine learning trains on thousands of faces, clear, obscured, hidden. It learns the patterns, the geometric relationships. And it can identify a face even when you can't consciously see one. Reanalyzing historical data. Visualization of archival SETI data. Terabytes of information. The camera zooms into the data, showing billions of data points. AI algorithms are applied retrospectively. Patterns that were invisible before now appear highlighted in the data, like constellations appearing in the night sky. Dr. Andrew Simeon, director of Berkeley SETI Research Center. One of the exciting possibilities is that the signals might already be in our archive. We've collected decades of data. Now, with AI and our new understanding of signal broadening, we can analyze that data with completely different eyes. We might find something we missed the first 1,000 times we looked. Technological hope. This is the pivot. This is how we've learned to look. Not for needles anymore. For broad strokes. For patterns hidden in complexity. We're not starting over. We're widening our vision. A new hope. For the first time in human history, we have a coherent understanding of why the Great Silence might not be the absence of signals, but the absence of proper listening. The fog between us and them isn't proof they don't exist. It's a problem we can solve. Human endeavor. Quick cuts of SETI researchers at work. Scientists collaborating. The global network of telescopes. People in classrooms, learning about the search. The tone is one of collective human effort. Determination. Hope. Dr. Jill Tarter, former director of SETI Institute. The silence isn't failure. It's an invitation. An invitation to understand better, to listen more intelligently. We're closer to finding an answer now than we've ever been. And that answer might come from data we've already collected, using tools we've just invented. Future telescope network. In the coming decades, we'll deploy more sensitive instruments. Larger arrays. More sophisticated AI. We'll scan more of the sky, in more detail, with greater sensitivity than ever before. And we'll listen, not just for silence, but for the signal hidden in the silence. Cosmic perspective. Somewhere out there, around an M-dwarf star, perhaps on a world in the habitable zone, another civilization might be broadcasting the same question we ask. Is anyone listening? Their signal, distorted by the cosmic fog, might be traveling through space right now. Passing by radio telescopes. Hidden in the noise. Waiting to be found. Earth and sky. The silence isn't proof of absence. It was just a problem of focus. And now, with clearer eyes, with better understanding, with new tools at our disposal, we are finally adjusting our lenses. A distant signal animation of a weak, broadened radio signal, almost lost in noise, suddenly highlighted and isolated. Clear. Unmistakable. A single thought appears on screen, and now, the sky is about to get a lot louder. Do consider subscribing the channel for more such interesting content which help us to work effectively. Thanks for watching, we'll see you soon.